It turns out, let me give this system a name. So I usually use a capital letter to designate the name of the system. And soon we'll learn that with a small letter h, I define a function, a discrete time function, that characterizes the system completely. So let's see what I mean by that. Suppose the input signal is the Dirac delta. I'm sorry, not the Dirac delta, the Kronecker delta. As you know, I always have a few minutes of booting up at the beginning of lecture. When you apply this Kronecker delta to a system it'll have some response. We call this response with the small letter h. So in this case, y of n will be h of n. H of n is some function of time, some discrete time function. Some discrete time function. Okay? For systems that are LTI, linear and time invariant, this output corresponding to this very special input has a special name. We call it the impulse response. Of the system. Now, any arbitrary system will have some kind of a response to an impulse input. For those general systems, we say the response of the output would be the response of the system to the impulse. But the phrase impulse response we reserve specifically for linear time invariant systems. Systems that satisfy the superposition property and the shift invariance or time invariance property. So if I tell you that the impulse response of a system is small h, you automatically can assume that I'm talking about an LTI system. Now, why is this delta and why is this h so important? Let's see. Well, if you happen to know the response of the system to this special input, I can give you any arbitrary input signal, x. Let's say it's 1, 2, 3. 0, 1, 2. And it's, let's say, 0 everywhere else. Okay? I tell you now, I send this through exactly the same LTI system. Can you tell me what the output is? Any ideas on how I can approach this? You know the system is linear, and you know the system is shift invariant or time invariant. Yeah? Okay, stop. Tell me how you're getting that. Reason your way through. Okay, pause. So, what's your name? Andrew. So, Andrew is going back to one of the things that we've already done in this class, which is to break down this signal into a linear combination of shifted impulses. Okay? So, x of n can be written as, can you give it to me in algebraic form, and then we'll do it graphically. Delta n times 1 plus 2 delta n minus 1. That's this lollipop right here. Yep. Plus 3 delta n minus 2. Okay? Is everybody with us? We've done this breakdown of signals into a linear combination of impulses before. And now you're beginning to see why we've been doing it. So graphically, x of n would correspond to a lollipop scaled by 1 at the origin, plus a lollipop scaled by 2. Let's put the 1 here. This one is at 1, plus a lollipop scaled by 3, so this is 3 delta n minus 2. This is 2 delta n minus 1. And this is delta of n. And the sum of these gives you x. Okay, Andrew. Take it from here. Let me go here. Yep. Right. So the system is linear, which means the response due to x is the response due to this component, or this term, plus the response due to this component, plus the response due to this component. Is everybody with me? All right. Now, what's the response due to this guy here? H of n. This is just delta of n. I haven't scaled it by anything, so it's h of n. Okay? So the output is h of n. What about the response due to this one? Okay, so Andrew says the response due to this is 2 times h of n minus 1. There are two things that he's using here. One is the fact that you can scale whatever the response is due to this delta n minus 1, the shifted impulse, by 2. What property of the system are we using to do that? Linearity. So if the system is linear, it has the scaling property. Whatever the response is due to the plain old impulse at 1, and we don't know what that is yet. Right? We don't know what the response is due to the shifted impulse. We know the response due to the unshifted impulse. But we don't yet know the response due to the shifted impulse. But whatever it is, when you put a 2 in front of it, you scale that response up by 2. Now, how do you find the response, or how do you argue your way to finding the response due to the shifted impulse? Andrew, what property are you using? Time invariance. If the response due to delta n is h of n, when you shift that delta n to the right by 1, you shift that h to the right by 1. So now we're using two properties to figure out the response due to the second component. So you get 2 times h of n minus 1 plus. And so the rest of you now. What's the response due to this guy here? 3h of n. H of n what? Minus 2. Okay? If I put that 1 here, you will notice that this is simply x of 0. This is x of 1. And this is x of 2. If x had other lollipops in its description, those two would be sitting here as coefficients, and you would have had appropriate shifted versions of h. Okay? So if you were to write this in more generic form, you'd have, potentially x would have lollipops going all the way back to minus infinity and extending all the way to infinity. You'd have things like x of minus 2, h of what? N plus 2, plus x of minus 1, h of, plus x of 0, h of n, plus x of 1, h of what? N minus 1, and so on. You got to make sure you get the relationship between the argument in x and whether or not you have a minus or a plus here straight, because you can easily mess that up. I can write this in a closed form. It would be m equals minus infinity to infinity. The value of xm times h of what? All together. N minus m. Congratulations. This, as you've probably seen in this week's problem set by now, is called the convolution sum. It tells you the relationship between any arbitrary input and the output of an LTI system. An LTI system, therefore, is completely characterized by its response to this innocuous signal, the delta at the origin. If you know the response of an LTI system to this signal, you can figure out the response due to any arbitrary input signal x. And that's one of the beauties of LTI systems. We have a notation for convolution. So when we have it, the expression in that form, we say y of n is x star h whole thing of n. When you read other textbooks, a lot of other textbooks use this notation. Y of n is x of n star h of n. We don't use that in this class. It's confusing. Because convolution is an operation on signals, not instantaneous values of those signals. Okay? We'll do an interpretation of this soon. Now, a lot of times, you'll bump into summations of this form or even integrals. You can see that this summation will turn into an integral when we take the story to continuous time. When you have combinations of variables, you can always use substitution to convert the summation into an equivalent form. So if we let L be n minus m, then I can write the output as a sum over all L. If m is going from minus infinity to infinity, then so is L. And in the case of summations, we don't have to worry about which one goes in the bottom, which one goes in the top, because we're summing a whole bunch of values. What happens to the h? H of what? L. What happens to the x? Do it fast and tell me. N minus L. Okay? This we call the convolution of h and x. So the fellow with the simpler argument comes first. The one with the more complicated argument comes second. Now, because we changed variables, the output written in this way must be identical to the output written in the way on the other board. So what can you tell me about convolution? It's commutative. Remember, a system is a function. You can't give it an input signal and get one response according to one formulation and a different response according to a different formulation. A system takes one signal and produces only one corresponding output signal. It doesn't map one signal to two different output signals. So it must be the case then that x star h is equal to h star x, which means convolution is commutative. just like addition, just like multiplication. Now, at this point, I've got to give you a little lesson in, far be it for an immigrant like me to give you a lesson in English. The verb for convolution is not convolute. It is convolve. And you'd be amazed, even after 5 times of my saying so in class, how many of you will still say it on your exam. I convolute the signal with another. I'll give you a convoluted grade. So you convolve 2 signals. Convolve, convolving, convolved. Have convolved, had convolved. There we go. All right. You want a break? Yes? Fine by me. Okay, so let's go back to this example. In this example, I haven't given you what the impulse response is. So let me give you an impulse response. Suppose in the previous example, let the impulse response be this. Minus 5, and let's make this 5. And it's 0 everywhere else. So this is h of n. What I want you to figure out is the output for that particular input of this LTI system. How would you go about doing it? Find the output of this system in response to How would you do it? What I want you to think about, does everybody get this down? I want to bring down the other board. Notice you have a choice of which one of these signals, H or X, you take, and you shift by an amount M and scale by the other signal values. So when you want to figure out the output corresponding to this system, you can write the output either as the convolution of X with H or H with X. If it's X with H, you would have, how many values do you have? X0 times what? Hn. Plus X1 times what? Hn minus 1. You got a deja vu feeling? X of 2 times H of n minus 2. If H of n is this, what's H of n minus 1? Well, this thing shifted to the right. And h of n minus 2 is shifted to the right by 2 samples. So that's one way to do it, if you want to do it graphically. Another way to do it is to look at that form of the convolution and write h of what? H of negative 5 times x of n plus or minus n plus 5 plus h at 5. Basically, you pick all the non-zero values of h plus h of 5 times x of n minus 5. Which one's easier to do, this one or this one? Huh? The second one. So do it. Look at x of n plus 5. What does this mean? You take that diagram, and what do you do with it? Shift it to the left. Multiply it by h of minus 5. I've picked that to be 1 for you. So it'll be straightforward. And then you do the same thing with x, except now you shift it to the right by delaying it, and you scale it by h of 5. And you add those two together and tell me what you get. So you're beginning to see some of the implementation issues. This one involves 2 multiplications and 1 addition. This one involves 3 multiplications and 2 additions. This one's clearly more efficient for this particular case. And when you have to do things by hand, after you get some practice, you'll figure out which one of these forms to use that makes your life easier. So go ahead and do that. You ready? No? Yes or no? Okay. Meatball. You are? I'm Michael. Michael. So what do I do? What do I do with this? How do I plot that? No, I thought you were dealing with this one. Aren't you dealing with the first term? Yeah. Okay, so it's not h of 5, it's h of minus 5. 1. So, very good. So this is x of n plus 5, and we're scaling it by h of minus 5, but h of minus 5 is 1. Okay? Mm-hmm. Okay, so this is 5, I believe. Let's see, 1, 2, 3, 4, 5, 6, 7. Negative 1, negative 2, and then negative 3. And the rest of the values are 0. Okay, so this is the output. Now, if you wanted to do it with this method, with this form of convolution, you would have had to do more work. You would have had to shift h to the left, and you would have had to delay h twice, scale it by these numbers, and then add them all up. So this form was simpler. This way of writing the convolution or doing convolution is unique to discrete time convolution. It's a nice formulation. So when we deal with this method of convolving signals, we call this the echo model of convolution. This is not standard terminology. This is a mnemonic that I use to think of what we are doing. Strictly speaking, you're not dealing with echoes. Echoes are always delayed. In this case, you have x of n plus 5 and x of n minus 5. So x of n minus 5 is really an echo. But this is, you can think of it as an echo in the opposite direction. But essentially, you view convolution as a linear combination of echo versions of a signal. Only one of the two signals gets echoed. So in the second formulation, it's the x that you're echoing. You delay it by 5, you advance it by 5. So those are the two echoes. And then you linearly combine them based on values of the other signal. In the first formulation, you have echoes of the impulse response viewed as a signal. So you have the undelayed echo, unit delayed echo, and the twice unit, two-sample delayed echo of h. It's much harder to do this. It doesn't make a whole lot of sense to talk about this echo model for continuous time systems. Because for continuous time, it's how much do you shift to the left and to the right. It's a continuum of shifts. It's much easier to imagine it in discrete time. Bonsai! About time. is slightly more complicated when you want to do it on paper, but it's important to know this. If you look at this convolution expression here, y of x is h of L x n minus L, that linear combination. Let me rewrite that here. Summation over L of h of L x of n minus L. You have two functions written in terms of the generic variable L. So if I were to do that, I would have L at minus 5 is 1, at 5 is minus 1. This would be h of L. Okay? The question is, how do I draw x of n minus L when L is my dummy variable? How do I draw this? This is confusing at first. It certainly confused me when I was first learning about this, probably before many of you were born. So let me go over that, and then we'll go on to a website if the computer doesn't crash on me again, and the internet is connected. And we'll see demos of this using Java applets. There's a place at Johns Hopkins University where they have Java applets of these convolutions with sample signals that you can play around with and get to learn this method better. So I want to plot x of n minus L. When L is the dummy variable, n becomes a number. Okay? So here's the scheme. To plot x of n minus L, first flip, then shift. When I was learning convolution, Karate Kid had come up. And Mr. Miyagi, I don't know if you've ever seen that movie. Wax on, wax off. So the way I finally injected this into my head was flip, shift, flip, shift. So here's what you do. I should say step 1, step 2. Let's go to step 1. You start with x. Plot it as a function of L. Just straight x, just like that. So here you'd have 1, 2, 3. 0, 1, 2. 1, 2, 3. Dummy variable is L. This is x of L. Okay? So the way I do the flipping is I use my favorite trick, which is the hat trick. I define a new signal x hat, which is the flipped version, or time-reversed version of x. So when I plot that, I have 1, 2, 3. 0, minus 1, minus 2. That's x hat. You with me so far? Now, from this x hat of L, I want to produce, this is where the shifting comes in. This is step 2 now. So that was step 1. Step 2, shift. And what we want is x of n minus L. So here's what I'm going to ask you. By what amount and in what direction do we shift? Do we shift x hat to get x of n minus L? Obviously, there are two cases. when n is positive and when n is negative. But algebraically, what do I have to do to x hat to get x of n minus L? Let me actually do the two cases after I write the expression. So, only two possibilities, right? It's either x of L minus n or x hat of n minus L. Oh, I'm sorry. X of L minus n or L plus n. Which one? When you look at the relationship between x hat and x, which one of these will produce x of n minus L in the top there? Who says the first one? Who says the second one? Well, let's do it. X hat of L is x of minus L. Okay? So x hat of L minus n is wherever you see an L in the right-hand side, you replace it with L minus n. Right? Minus L minus n. What do you get? X of what? N minus L. Let's take another poll. Who says the first one? Who says the second one? He's just trying to be a contrarian. Notice what happens if I look at x hat of L plus n. Then every place I see an L in the right-hand side, I replace it with L plus n. So that's x of minus n minus L. It's not what we want. Okay? So, now we consider the two cases, n greater than 0 and n less than 0. You've started off with x. You flipped it. Time reversed it. If n is greater than 0, what are you doing to the flipped version? Are you delaying x hat or advancing x hat? Delaying x hat. So for n greater than 0, x of n minus L is a delayed version of x hat. In other words, you flipped it, you flipped x to create x hat, and now you delay it. You shift it to the right. So when n is positive, after you flip, you shift to the right. When n is negative, after you flip, you shift to the left. It's the opposite of what you would normally do with a signal. Okay? And that's because of the flipping of the time axis. So let's do that for this example. This, by the way, is something that's ordinarily done by computers these days. But you should be able to do it by hand for very simple examples. So here we have x, which is that. So x of L, we plotted 1, 2, 3. 1, 2, 3. L, x of L. You flip it. 0 minus 1 minus 2. So this is x of minus L. And then let's say n is and you want to figure out what x of n minus L is, which is x of 1 minus L. What do I do to this? Just tell me what you would do with this signal. This, by the way, is x hat of L. Oh, wrong axis. What would you do with that signal? This way or that way? To the right. So I take that, and now I'm at minus 1, 0, 1. 1, 2, 3, L. Okay? And for n equals minus 1, what do I do to this? I go to the left. So I have my 1, 2, 3, minus 1, minus 2, minus 3. So let's say explicitly this is x hat delayed. This is x hat advanced. It's critical that you do the flipping before you do the shifting. Otherwise, things are going to get messed up. Now, you want to do this convolution. So you're asked to do all these possible shifts, x of n minus L. N now has to go from minus infinity to infinity. That's a pain if you have to do this. But when you shift, this signal, when you're shifting it to the left, and you have to multiply this is x of n minus L. You got to pointwise multiply this with h of L. That's what's going to save you. Because as long as the shifted version of, flipped and shifted version of x doesn't overlap with h, you're going to get zeros. So what is the first n? What is this first n for which this flipped and shifted version, or the other one? So now I start n equals minus infinity, and I start sliding. What is the first value of n for which this overlaps with h? Where is h? Here. What is the first value of n? So remember, I've taken this signal, I flipped it, and I shift it to minus infinity for n, and I increase n as in Nancy. I increase it. At what point, as I increase it, I'm shifting to the right, toward positive infinity. At what point will this sample overlap with this sample? Negative 5. So here I have h of L, which is 1 at minus 5 and minus 1 at 5. This is h of L. I have x of n minus L. So if you were to draw x of n minus L, you know it's going to be a flipped version of x. Where would this be? This front lollipop. Where would this be at? No, for n, just a generic n. It would be at n. So this would be at n minus 1, and this would be at n minus 2. Right? So for what value of n will this, I'm taking the pointwise product of these two. For what value of n will this overlap with that? Negative 5. And at that point, what's the product of the two signals? So for n equals minus 5, x of, or h of L, x of n minus L is, what do you get? 0 everywhere except at negative 5. And the value there is 1. Then you've got to do, so, and what's the output for that particular value of n? What does that convolution sum say? You've taken the pointwise product of these two signals, and now you have to sum over all the values of that product. That means I'm summing over all these values. What do I get? 1. So y at minus 5 is the sum over all L of h of L pointwise multiplied by x of 5 minus L, which is this guy when n is 5. What value do you get? What do I get when I sum all these values? Everything is 0 except that one. So y at minus 5 is 1. Is that what we had before? Now we want to find, I'm just going to do one more sample because this is a pain in the neck. I'm going to do one more sample and then you'll get the idea. And then we'll go to the simulation because then that's going to be much easier to visualize. Y at minus 4 is the summation over all L, h of L, x of 4 minus L. Okay? What is x of 4 minus L? So this is 4. 3, 2. This is x of 4 minus L. Okay? Multiply this by h of L. This is, oh, then negative 4. I'm sorry. Negative 4, negative 5. Negative 4, negative 5, negative 6. Multiply this by h of L. What do you get? What's the product? What happens when you multiply this with that signal, h of L? How many non-zero values? 1. Where? Negative 5. And what's that value? 2. So this is x of 4 minus L times h of L. Okay? The convolution sum says take this product signal and sum over all its values. What do you get? 2. So that means y at minus 4 is 2. 2. Much more painful way of doing convolution, this flip and shift. The echo model is much easier to deal with. So now let's see this in simulation. Okay. So you can get here from the resources section of the Ptolemy website. You click on resources, and then you go to Applets Illustrating Convolution. And this takes you to Johns Hopkins University, and there's a Joy of Convolution for continuous time and for discrete time. So we go to discrete time. You got to have Java running on your machine. So on the left you have X, an input signal, and H, a possible impulse response. And you have a choice of what signals to select for this convolution. So let's say I pick this one, okay, the square pulse in discrete time. And let's say I pick this decaying one-sided exponential as my impulse response. Can you see in the back? Should I turn off the lights more? Okay. So now you just go here on the second. So there are 3 rows beneath the section where you pick your signals to convolve. Here you click, and notice in this box right here, you have the flipped and shifted version of X. On this box right here, you have H with the dummy variable K. We use the dummy variable L, they're using K, it doesn't matter. So H plotted as a function of K. It's a one-sided decaying exponential. N here is minus 16. So it took the box function, flipped it, and so this, what I'm looking at here, is X of minus 16 minus L. That's what I'm looking at. Minus K, sorry. X of minus 16 minus K. So you flipped. This is, if I go one sample to the right, it'll be X of minus K, flipped version of X. As N goes negative, I'm going to the left. So you want to figure out what the output is from minus infinity to infinity. That's the convolution sum. Okay? In this case, the signal X is the one that's being flipped and shifted. You want to figure out Y from minus infinity to infinity. So you start with the most negative N you need to start with. As I increase N, notice there's no overlap between the green signal, which is the flipped and shifted version of X, and the blue signal, which is the impulse response. I'm not going to have an overlap until when? 0. So the output signal is going to be 0 all the way until 0. This third row here in yellow is the pointwise product of this green box and this decaying exponential. As long as they don't have an overlap, this yellow signal is going to be 0. When I come to n equals 0, then the product has an overlap. And it's in this unfortunate color yellow, which I'm not sure if it's showing near the back of the class. But now you have one lollipop of the green signal and one lollipop of the blue signal multiplying. Everything else is 0. So you have a lollipop at the origin. The convolution sum says, take this pointwise product and sum over all the non-zero lollipops. Well, there's only one non-zero lollipop, and that's the same as what shows up in the bottom. Now, when I shift to the right, do you expect the output to increase or decrease? Increase, because now I have more than 1 point of overlap. So let's go there. Now you have 2 green lollipops overlapping 2 blue lollipops. You pointwise multiply, so you get these 2 lollipops in yellow. And the convolution sum says, sum over all these values. Well, you sum the height, this lollipop plus this lollipop, and that gives you this red lollipop at n equals 1. Notice the variable in the bottom row is n, Nancy. Okay, that's because we're figuring out the value of the signal at the output at samples n. These 2 are dummy variables k. Now, if I shift to the right, one more. Now I have 3 lollipops overlapping. So I have 3 yellow lollipops here. I have more to add. and that's why the red one goes higher still. And finally, I have 4 overlaps. I have 4 non-zero values in the yellow, which is the pointwise product. And I have slightly more, a slightly greater lollipop here. What happens if I go one step further to the right? Do you expect it to decrease or increase? Decrease. And that's exactly what happens. So you keep doing this, and I slide all the way out, and it decreases as the overlap between these and the decaying exponential goes down to 0. So this is the output of the LTI system described by this impulse response and this input. You can also change the signals that let's do it with exponential and an exponential. Okay? So now I click here. Notice it's flipped this green exponential, the input. And I'm starting at minus 17. I'm not going to have any values in the output until n equals 0. That's when this green signal and the blue signal are going to have an overlap. Yellow lollipop. To the right, I have 2 overlaps. So I have 2 lollipops here. I go to the right more, to the right more. And there you go. You've got the corresponding output described here. If I have a box and a box, so the impulse response is this box. The input signal is this box. Box and box usually gives you either a trapezoid or a triangle after you convolve. If the lengths of the 2 boxes is the same, namely in here you have 4 samples, you're going to get a triangle. If one of them is longer, you're going to get a trapezoid. Well, let's see what happens. So when you time reverse this box, because this is symmetric along its value, non-zero values, you get the same box back. But actually, this value corresponds, this spike corresponds to this one. This one corresponds to this one. This leftmost one corresponds to this rightmost one. So I flipped and I'm shifting. Let's go down and see what happens. I shift. 1 overlap, 2 overlap, 3 overlaps, maximum overlap. And then it starts sliding off at the other edge. Okay, that's a triangle. In continuous time, you can see this much better. But I encourage you to play around with this Java applet to get a feel for what it's like and what it's like to do convolution. Now, there are some crude rules of thumb about doing convolution with this flip and shift. If you can do it in discrete time with the echo model, do that. It's much simpler than this flipping and shifting. But if you don't have a choice and you have to do the flip and shift, I usually pick the signal that's easier looking or simpler looking to flip and shift. If the signal is too complicated, you don't want to be flipping and shifting that one. It's not a hard rule, but most of the time it works. Pick the simpler one to flip and shift. So if I were to do the convolution of a box and an exponential, I'd keep the exponential fixed, and I'd flip and shift the box. So that's easier to do. As opposed to having the exponential here and the box here. You know you're going to get the same result if you reverse the roles of the box and the exponential, because convolution is commutative. But it's going to be more difficult keeping track of a more complicated looking signal when you flip it and shift it. So now you're going to be flipping and shifting the decaying exponential. And you don't want to do that in general. Okay. So that's about all I want to say about convolution. The best way to learn it is to do practice with it. Now we have a few minutes. I want to go into the, just give you an idea of what's coming up next. Just to recap, we studied the impulses because knowing the response of an LTI system to an impulse tells you everything you need to know about the system in terms of the output. So you can give it an arbitrary input, break the arbitrary input into a linear combination of impulses, use linearity and time invariance properties of the system to figure out what the output is. And what we've been doing are two graphical ways of figuring out the output given an arbitrary input. But remember, we also studied complex exponentials. And there is a reason we studied those. Again, it has to do with LTI systems. What's so special about complex exponentials? So, complex exponentials and LTI systems. Notice I'm skirting the whole topic of continuous time convolution. If you thought this was a pain in the neck, you should think about what a pain continuous time convolution would be. So I have an LTI system. I call it H, impulse response small h. Output Y, input X. Y of n is the convolution of H and X. Okay? We've already studied how the system responds in a special way to a Kronecker delta applied to its input. Now, let's look at the input signal, which is of this form, e to the I omega n, a complex exponential of frequency omega. What happens when I plug in this input signal, apply this input signal to this LTI system? Let's plug it into the convolution sum. This is our foray into digital filtering. So if x of n is e to the I omega n, I have x of n minus L in the summation. So what is x of n minus L? What do I do? E to the I omega what? N minus L. Wherever you see an n, you replace it with n minus L. Okay? Now plug that into the convolution sum. Y of n is summation over L, H of L, e to the I omega n minus L, which I can break up and say e to the I omega n and e to the minus I omega L. Okay? The summation is over what? This is a function of n and omega. It has no dependence on L, Larry. So I can pull it out. So what's inside the summation is L, H of L, e to the minus I omega L, this whole thing times e to the I omega n. Now that's neat. Look at the summation. I have a function of L and a function of omega and L, and I'm summing over all L. What's going to come out of this summation? A function of what? Omega. It's the only variable. I'm summing over all L, so after I do the summation here, I'm not going to have any more L's in my expression. I call this H of omega. Okay? This is called the frequency response of the LTI system. Although on the blackboard I use the same capital letter H to name the system and to also refer to its frequency response, in print I will actually use different fonts. So this H will be a normal math script. That H is, in print I use a sans serif font, so that corresponds to the name, and this corresponds to the frequency response. There's a relationship between the impulse response and the frequency response, and that relationship is given by this, the summation over all L, h of L, e to the minus I omega L. Impulse response and this is frequency response. You will learn later that this H is the Fourier transform of this H. But you don't know that already yet. Right now, all you know is that this frequency response is defined based on the impulse response. This is where we now have our first interface between the time domain and the frequency domain. Remember at the start of the semester I said we live in two parallel universes that touch every now and then. And you've got to be able to hop from one to the other. So this describes the time domain behavior of the system. This characterizes the frequency domain behavior of the system. Notice what's happened. You sent in a complex exponential in. You sent in a complex exponential, and you got the same complex exponential at the output. E to the I omega n went in. And h of omega, which is some complex quantity, e to the I omega n came out. So if I send in, for example, e to the I pi over 4n, I get out h of pi over 4, e to the I pi over 4n. This frequency response tells you how the system treats frequency omega. And this is where we have a filter. It's kind of like a sieve, except the sieve allows some particles, in this case, which are analogous to the frequency, some particles to go unscathed, and it kills some other, traps some other particles. In digital filters, this h of omega tells you how much the filter amplifies or attenuates the frequency omega. Your equalizer is essentially this, where each knob corresponds to h for a particular frequency band. You want to turn down the bass, you have an h of omega filter that kills low frequencies. So h of omega will be low in magnitude for those frequencies. You want to amplify certain frequencies, you make sure that your filter has high magnitude for those frequencies. And that's where we now have the discussion of filters. And next time I'm going to do some plotting and graphing and show you some simple discrete time filters.